these two problems because we're going to see this throughout the lesson today. If I have a triangle with three sides and it's a right triangle, what would I use to find R? Good. Yeah, good old Pythagorean theorem. This is where we label this A, B, and C. If I know 2 out of the 3 sides and it has to be a right triangle, then I can do A squared plus B squared equals C squared. So this one's pretty straightforward. (12 squared would be 144. 13 squared would be 169. So that gives me R squared equals 25. So R would be 5. Take the square root of 25. Okay, we've done one like that before. Just kind of a reminder of what we would use there. We're going to see the Pythagorean theorem used a lot the rest of the year. Okay, and there's going to be different times where it's going to show up. On the one here, it's a little bit different because we have 2 unknowns. We don't know this side here, and we don't know this side here, but I know that this side is 4 units longer than this side. So if I said this was 6, then this would be 10. We just don't know what it is. So what we have to do is we have to figure out what that would be. And here's how we're going to go about that. R squared plus 8 squared. Okay, those are my 2 legs, the 2 sides that touch the 90-degree angle. And then the hypotenuse is always the longest side. It's also the side opposite the 90, equals, and here's where you got to be careful. We have R plus 4 squared. So we got some algebra skills that are going to go and play here. If I have R plus 4 squared, when I square something, what am I really doing? If I squared 7, for instance, what would I do if I had 7 squared? Multiplying 7 by itself, right? So if I have R plus 4 squared, this would be R plus 4 times R plus 4. Okay, what are we going to have to do here? We haven't seen this for a while. It's FOIL. Yep, it's good old FOIL. First, outside, inside, last, or distribute. If you just want to remember it by distributing, I'm going to take R times both of these. So that would be R squared plus 4R. And then we're going to take 4 times both of those. So that would be 4R plus 16. And we're going to see some problems that have this today. The most common mistake here is people will see this and they'll square the R and they'll square the 4, but they'll forget the middle parts, the outside and the inside parts. Okay. So this really becomes R squared plus 8R plus 16. But it's been a little while since we've done FOIL. When I write my equation now, I'm going to say R squared plus 8 squared equals what we just got when we FOILed. R squared plus 8R plus 16. Okay, now our goal is to get R by itself, just like always. The good thing here is that we have an R squared on both sides. So those R squareds can knock each other out. 8 squared is 64. And now we just have a basic old 2-step equation, trying to get R by itself. So I would subtract 16. And then I'd divide by 8. This side here would be 6, which means my hypotenuse would be 10. Okay, so there's going to be some algebra stuff involved. That's one of the reasons why we take Algebra 1 before we take geometry is we got to be able to do some of those algebra skills within geometry. We've been solving equations all year long, but now we're going to see some things like that pop up. Okay, in this part right here, we're going to talk a lot about vocab. We all know what a circle is, okay? But you may not, like if I said define a circle, then that would be a little bit harder to do, right? we know what it looks like, but how is a circle made? Well, a circle is a set of points in a plane that are all equidistant from a given point called the center of the circle, okay? So we have this point right in the middle of this circle here, and every line that I draw here is going to be equidistant from the center. If I go from the center to the edge of the circle, all of the points here would be the same distance away from P. Whether that's 4 or 3 or whatever that length is, they're all equidistant. They're all the same distance. Okay, and that's how we can make a circle. We can go all the way around that circle. When we write this, we name the circle by its center. And so we call this circle P. P is the center of the circle, so that would be the way that we name this circle. Okay, a lot of these words, or at least some of them you've probably heard of before. The first one is the radius. The radius is the segment that goes from the center to the edge of the circle, anywhere on the edge. Okay, we only have one radius drawn in here. We could draw a bunch of them, kind of like I did on that picture before. A segment whose endpoints are on the circle. So this is probably one you've never heard of before. This right here is what we call a chord. The two endpoints of that chord are on the circle. Okay? And so we call this a chord. That's one that's probably going to be new to you. Diameter is one we've seen before, I think. Diameter is all the way across the circle, but it goes through the center. Okay, it contains the center. So basically, the diameter is a chord. It's just a specific type of chord that goes through the center. So that's the only difference between this and the diameter, is that the diameter goes through the center. Okay, the chord does not. It doesn't have to go through the center. If it does, it's called the diameter. So it's a little bit more specific. Okay, a secant is kind of like a chord, but it continues on. So instead of a segment, it's a line. And a line goes on forever. We talked about that way early back in the beginning of the year. A chord has two specific endpoints, whereas a line goes on forever. So a secant is a line that goes on forever, and it intersects two places on the circle. So for instance, this one, it crosses or goes through the circle at those two places. Two intersection points. Okay, a tangent, and I will tell you this is different than the tangent we talked about in the trig chapter. Okay, that tangent was tangent of a triangle. This is the tangent of a circle. The tangent is going to touch a circle at one distinct point. So basically the way I think of it is it kind of just scrapes right along the edge of that circle. Okay, it's not going to go through the circle, it's just going to come right along the edge of the circle. So that is what we call a tangent line. Once again, it goes on forever. It has arrows on either end, and so it would continue in both directions. And then finally, point B right here is what we call the point of tangency. That is where that line intersects the circle. It only touches it at one point. It intersects it or touches it at one distinct point. Okay, so those are words that we're going to use a lot as we go throughout chapter 10. And so we got to make sure we're familiar with those. Okay, on the next page, we are just identifying what we have. Okay, we're just going to name it, and there's two questions that it's asking me here. First of all, is each one a line, array, or a segment? And secondly, which one of those special types of terms is it? Okay, so first of all, AC. All we have to really pay attention to here is our symbol. Is there any arrows on that? Do we have, no arrows above AC, right? So that means it stops at a specific point. It stops at A and C. Those are my two endpoints. So when I talk about AC here, I'm talking about this piece right here. It's not going to continue on. And that's why it's important to understand that and know that. If I had arrows, then it's going to keep on going. But this one is not. So this one is a segment. And that segment is called the radius. Two distinct endpoints. Okay, AB. Start at A, all the way to B. A and B are both on the circle. It goes through the center. It's still a segment. This segment is what we call the diameter because it goes through the center. Okay, part C, we only have one arrow, okay? The first two did not have an arrow. This one only has one. What do we call a figure that only has one arrow? That's a ray, okay? So I'm going to start at D. I'm going to go through E. So basically I'm saying this right here, starting at D, going through E. This would be a ray, and it touches the circle at one point. B is the point where it touches the circle. So we would say that this is a tangent ray, or a ray that is tangent, however you want to say it. This could be a segment, it could be a line, or it could be a ray. That's why we're identifying the differences here. Okay, AE has two arrows. So that means that it's a line. And if I look at that line, a line continues on forever. How many times does that line touch the circle? Twice. Okay, so we would call that a secant line. Oh, I put it on the wrong one. That's my fault. Okay, AG. Okay, AG. Notice there is no arrows here. So we're starting at A and we're ending at G. We're not continuing on. So this is a segment. And this segment is what we call a chord. It's not a diameter because it doesn't go through the center. Diameters go through the center, like this one here. This one does not go through the center, so it's just a chord. Okay, and then the last one, CB. CB starts at C, stops at B. So it's also a segment. And we call that the radius of the circle. A radius only goes halfway from the center to the edge of the circle. Diameter goes all the way across. Okay, name a tangent of circle C. Okay, and just remember we call this circle C. So when I read that out loud, okay, we're calling it circle C. And there's a lot of different ways I could name this. This piece right here could be named a lot of different ways. Easiest way to name it would be line DE. Or I could call it ray ED. Up above, we did ray DE. Now this is ray ED. I'm starting at E. I'm going through D. I also could just do DB, segment DB. So it could be a line, a ray, or a segment. All of those touch the circle at one point. They touch the circle at point B. So that's how I know they're all tangent, because they only touch the circle one time. But it can be any of those types of figures, a line, a ray, or a segment. And so it just kind of depends on what they're asking for. If they say name a line that is tangent to circle C, or name a ray that's tangent to circle C, then you have to make sure you name it correctly. Okay, this page here is talking all about tangents, different types of tangents. First up, if we have two circles that are coplanar, that means two circles that are in the same plane. Okay, they could overlap, they may not overlap. In this case, the two circles are in the same plane and they're intersecting one another. They actually are intersecting at two distinct points. In this example, we have two circles, one smaller than the other, okay? But they are intersecting at one point. So here I would say that this circle is tangent to the other circle because they're only touching at one distinct point. Over here, I kind of think of this one as like a bullseye. We call those concentric circles, where a bullseye or a dartboard, for instance, you might have like different levels of circles, right? You got the outer ring, you got the inner ring, you get different points for each ring. Those are called concentric circles. They all have the same center, but they never overlap one another. They never intersect one another. None of the points on this circle are going to touch any of the points on this circle, but they still have the same center. They have a center in common. Okay, down below, we are talking about common tangent points, and those common tangent points can either be internal, which means they intersect the segment that joins the centers. Okay, and I'll show you how that works here in just a second. Or it could be external, where it does not intersect the segment that joins the two centers. Okay, so two questions down here. First of all, they're going to ask us how many common tangents does these two circles have. Okay, the first thing I'm going to do is I'm going to connect the two centers together. Those are not tangents, but I'm going to connect the two centers together because we're going to use that here in just a second. I could draw a tangent that looks like this. It's coming across and touches each circle at one distinct point. So they have a common tangent line. I could also do the same thing down here. So that would be a second tangent line. Now we haven't seen one like this before. Oops, that's not a very good picture. I could draw a line that looks like that. It touches both circles. It kind of scrapes by and touches both circles. And I could come by the opposite direction. And it's just scraping along the edge of that circle. So for this one here, we have 4 different common tangents. The first 2 that I drew are external because they do not cross this blue line that I drew in. This is the segment that connects the two centers. The other 2 that I drew go right through the middle of that segment. So these 2 are what we call internal. So this one has 2 internal and 2 external. Okay. And I'm just using the prefix to make it a little bit quicker. So you have 4 of them, and then we have to identify what type it is. Is it internal or is it external? Okay, each one of these pictures is a little bit different. We're doing the same thing. Okay, what type of tangent would these 2 be? Are those 2 tangents touching that segment, that blue segment? No. So they are both external. if I draw a tangent going like this, that goes right through the middle of those two circles, it could touch both circles at the same time, and it's also going through that segment, so this would be an internal tangent. So this one has 2 external, 1 internal. This one has 3. 2 external, 1 internal. Okay, this one here. I can't draw a tangent here that touches only at one point because, like, for instance, if I did this, I'm going through the circle at 2 points, right? So that doesn't work. It can only touch the circle at one distinct point. Each circle at one distinct point. So this one has 2 tangents, and they are both external. No internal. Hey, the 2 on the bottom, this line right here intersects both circles at the same point, okay? So it's still touching both circles at one point, it just happens to be the same point. It does not cross that little segment in between. This point is the center of the big circle. This point is the center of the smaller circle. That's why the 2 points are right next to one another. They're 2 different centers. One's for the small, one's for the big. This one is considered to be an external. So it has 1 external tangent. Okay. If I tried to do a tangent line for like the big circle here, is it also tangent to the small circle? Is it touching the small circle? No, because the small circle's on the inside. So there's no way that I can draw a common tangent line for those 2 circles. So this one has no common tangents. Okay, so just a lot of different scenarios, right? You just have to kind of draw some tangent lines and kind of see what it would look like. Okay, if we have a radius, QP, that intersects a tangent line, which in this case would be line M, then a radius and a tangent will always form a right angle, okay? So we have to know this is the radius, we have to know this is a tangent. If that's the case, then what we're going to say is that line M is perpendicular to radius PQ. Perpendicular, we've seen that word a ton throughout the year. Perpendicular means forms a 90-degree angle. And we see that 90-degree angle right here. That's why we're allowed to put that 90-degree angle there. Okay, so we're going to use that a little bit today to find missing pieces. And then on the bottom here, the second theorem for today. If tangent segments form a common external point, so here S is on the outside of this circle, right? That's why we call it external, because it is on the outside of the circle. P is on the inside, S is on the outside. These 2 points, RS and ST, both connect the circle to a common point on the outside. If that's the case, if it's tangent and it goes to the point on the outside, then I can say that these 2 segments are congruent. So I can say SR and ST are tangent segments, then SR is congruent to ST. Okay, and remember, it doesn't matter how you name it. I can say SR, you can say RS, and we're talking about the same thing. Same thing for ST or TS. Okay, so using what we just did there, okay, we want to prove that ST is tangent to circle P. Right now, we don't know. Does it intersect T at one distinct point? Kind of looks that way. We want to verify it. We want to prove it, okay? And so in order to prove this, then we want this angle right here to be a 90-degree angle, okay? Where the radius PT intersects the tangent TS has to be a 90-degree angle. If that's a 90-degree angle, then this will satisfy the Pythagorean theorem. This is where the Pythagorean theorem is going to come into play. These are my two legs. This is my hypotenuse. Bryson, what do you think we're going to do? Bet your phone's not going to tell you either. Let's put it away. Thanks. Okay, so this is going to be 35 squared plus 12 squared equals 37 squared. Okay, now we don't know if this is true right now, but if it is true, then we would say yes, it is tangent. If it's not true, then we would say no. So our answer here is going to be a simple yes or no. So let's do 35 squared plus 12 squared. What's that add up to be? Okay. And then 37 squared? 1369. And so here, this is just a simple yes. If those two sides are equal, then we have a right triangle, and therefore ST is a tangent to circle P. Okay. I'm not going to do the second one with you, but you got to be careful on this one here, because what would be the length of C to E? 2 is only the outside part, right? And remember, if this is the right angle right here, where the radius and the tangent meet, okay? Ryan, what do you think? 5, yeah. Because what's this little piece right here? It's the radius, yeah. So if this is 3, then this also here has to be 3. So we would do 3 squared plus 4 squared equals 5 squared, which is true. This equals 25. I said I wasn't going to do it, but now that we're here, they are both equal. You just have to be really careful about what's given to you, okay? And then it's just a matter of proving that it does work, that it does satisfy the Pythagorean theorem. Minutes ago, over here on this page here, we said these two segments would be the congruent, would be equal to each other as long as they're both tangent to one another. Okay, over here. Anytime they give me the radius here, CB has a length of r. That means this also has a length of r. Every radius in this circle would have a length of r. Okay? So when I set this up, we're going to basically do the same thing we did just a second ago. We know that the radius and the tangent have to form a 90-degree angle. And if that is truly a 90-degree angle, it does tell me here, this one we don't have to say yes or no. It already tells me in the direction that B is tangent to the circle. So we already know that it's tangent, but our goal here is to simply solve for r. What is the radius? Okay? So what we're going to do here, the first part, and this is where what we did at the very beginning of the lesson is going to come into play. So r squared plus 80 squared, those are my two legs, right? The hypotenuse, what would be the length of the hypotenuse? How would I write it as an expression? R plus 50. Okay. This whole thing right here is r plus 50. Okay. Would it be okay if I called it 50r? Is that the same thing? because 50r means we're multiplying 50 by r. Okay? So having a plus sign in there is a really, really big deal. Okay? And so when I write it over here, I got to go r plus 50 squared. And like I said, this is what we did at the very beginning of the lesson today. This part right here is not a big deal. R squared plus 6,400. Now usually what I like to do is kind of to the side or somewhere else where there's some space, is I'm going to have to FOIL r plus 50 times r plus 50. Okay? The more you do that, maybe you can do it in your head, okay? Or maybe you know what the process is and kind of can figure out what the answer is going to be. But not a bad idea to FOIL that if you're not real good at doing that. So this would be r squared plus 50r plus 50r plus 2,500. Most of the time you should be able to combine those two middle terms together. 50r and 50r would make 100r. So we got this big kind of nasty equation. The good thing here is right now it's what we call a quadratic equation because it has an r squared in it. But because I have an r squared on the left and I have an r squared on the right, if I subtracted r squared from both sides, the r squareds are going to disappear. So we don't have a quadratic equation anymore. Then I could subtract 2,500. The reason I'm subtracting 2,500 is because I want to get r by itself. The only place I have an r right now is over here. So 6,400 minus 2,500 is 3,900. And then we would divide by 100, and we get r equals 39. Okay, just for the sake of saving time, I don't think we're going to do this next one because it's basically the same thing. If you wanted to set it up, I'll just set it up for you, but I'm not going to go through the work and solving it. Just pay attention to where that 90-degree angle would be. Those are my two legs. Over here, the hypotenuse is going to be r plus 18. So this would be r plus 18 squared. And then from there, it's basically the same thing we just did, just a little bit different numbers. Okay, down here, r is on the outside, okay? Pay attention to the directions here. It tells me that rs is tangent at point S, so it's touching the circle at one point. It also tells me that rt is tangent at T. So what that tells me is both of those segments are tangent to the circle. One's at S, one's at T. And based on what we talked about here just a few, so I know this piece and this piece are congruent, which makes this pretty basic because all I got to do now is say 3x plus 4 equals 28. I'm going to subtract 4 from both sides. And I'm going to divide by 3. And I get x equals 8. The last one, basically the same thing. It tells me that M and N are both points of tangency. So once again, I know that these two segments are congruent. So it looks pretty basic. But there's something you got to watch out for here. We have an x squared. Right? X squared equals 9. It's just not x equals 9. It's x squared equals 9. How do I get x by itself here? Take the square root. Okay? So I'm going to take the square root of both sides. So my answer would be?
3.
Nope. whenever I take the square root of both sides, if I said, what number can I square to get 9? 3 is one of my answers, or negative 3. So it could be a positive or a negative 3. And it's okay for x to be negative. We're not talking about the actual length of the side. If I put a negative 3 in here, and if I square negative 3, what's a negative 3 times a negative 3? It's 9, right? So negative 3 can work. It is okay to get a negative answer for a variable. Not for a side length, but for a variable, it's okay.